Good evening. Welcome to the ninth lecture of this lecture series, Physics with Partha. In our previous class, we have seen heat as an energy, units of heat, principle of calorimetry, specific heat capacity, molar heat capacity, water equivalent, and then determination of specific heat capacity. Here we have seen one Reynolds apparatus. So today we are going to cover specific latent heat of fusion, intermolecular forces, measurement of specific latent heat of fusion of ice, measurement of specific latent heat of vaporization of water, and mechanical equivalent of heat. Okay. Let's talk about specific heat of fusion. So in the left hand side, the figure shows us phase transformation and the name associated with those transformation. We can see that solid phase is going to liquid, and this is the fusion. Then it absorbs energy and the liquid goes to vaporization. By this process, it goes to vapor phase or gas phase. Then it condenses to liquid and then solidifies. So in the solidification process, from gas to solid, it releases energy, and in the process of going from solid to gas, it absorbs energy. Now this energy is released or absorbed in the form of heat energy mostly. So for that we have some calculation. So let's calculate specific latent heat of fusion. So here it is written that heat supplied to a body, it can go to rise the temperature of the body, or it can cause a phase change. For example, solid to liquid, liquid to vapor, etc., etc. So during the process of melting or vaporization, melting means solid to liquid, vaporization means liquid to gas, the temperature remains constant. That means whenever phase change is happening, at that time temperature remains constant. Now consider a solid of mass m, amount of heat needed to melt is Q equal to ml. We have already learned this. Here L is known as for a given material, it is the latent heat, and it is a constant which is called the specific latent heat of fusion or latent heat of fusion. Now this is L is given per unit mass. So total ml will give you the total latent heat, and L denotes the specific latent heat. Now liquid changing to vapor, here also Q equal to ml, where L is known as specific latent heat of vaporization or latent heat of vaporization. Now when a vapor condenses or liquid solidifies, heat is released to the surrounding, or otherwise in the reverse process it is absorbed, but the amount will remain the same, like Q equal to ml. Okay, let's talk a little bit about intermolecular forces. As we know, in solids the intermolecular forces are very large. So this is due to lattice energy, and energy is released in the form of lattice formation energy. That is why they are strongly held together. Molecules are held in fixed position normally, and it is done in solid phase. But in liquids, molecules has a liberty to move around, but it can move only within the volume covered by the liquid. But in vapor phase or gas phase, the intermolecular forces are weakest, and the molecules not only move randomly, but they can move around the entire volume wherever they have been kept. Now when a solid melts, its molecules need to move far apart against the intermolecular interaction. So that needs energy to be supplied from the surroundings to increase the intermolecular energy of the system. Now internal energy for solid is less than liquid, liquid less than gas, and bond strength in case of solid is greater than liquid, greater than gas. Now let's talk about measurement of specific latent heat of fusion of ice. So here we have seen one calorimeter with a stirrer. So it measures, let's measure its weight, which is m1. So this is with stirrer in it. Next, measure its weight when we pour water on it, and it is m2. Next, we put a ice on that water body and we measure the weight of this whole thing. Then by subtracting those weight, we can particularly talk about the weight of those things, that is calorimeter, then water or ice. Next, we record the temperature in each step. Say initial temperature of the calorimeter and water was theta 1. Final is theta 2 after the melting of ice. Then temperature of the melting ice was 0 degree centigrade when it is put in the water. Then specific heat of fusion of ice is L, specific heat of material of calorimeter is S1, and that of water heat capacity is S2. Now in the next slide we will see the calculation. The calculation is nothing but heat loss equal to heat gained. So here all the term of lost heat is written. Heat lost by calorimeter in water in the calorimeter, then assuming no loss of heat into the surrounding, and heat is gained by the ice during the fusion process, and heat is gained by the water from melted ice from 0 degree to theta 2. So here we can write heat loss equal to heat gain m1 s1 theta 1 minus theta 2 m2 s2 theta 1 minus theta 2 equal to m3 into L m3 s2 theta 2. From there we can calculate the specific latent heat of fusion of ice as L equal to, like this, whole formula gives us latent heat of fusion of ice where all the other terms are known. Now latent heat of fusion is total latent heat. If we talk about, then it is m3L. Then let's talk about measurement of specific latent heat of vaporization of water. So this is also a specific kind of apparatus where we can see one calorimeter in the boiler, it is mounted, then temperature is to measure the temperature, thermometer is there, then whatever vapor is produced from this arrangement, it will go via a pipeline to a steam container. The steam is contained there and the lid is tightly bound, and the next outlet, steam outlet, here the steam will go out after it loses its temperature or loses its energy. Then another rubber tube is attached, so where it's again fixed to the calorimeter where temperature T2 is noted down. Then this is the final temperature, which is theta 3 after the steam becomes water. That means after releasing internal energy, it will condense. After the condensation, this water is found out. Okay. In the apparatus shown, the mass of the calorimeter was m1, which stirrer. Mass of water is m2, which is within the boiler. Then mass of condensed steam, the mass of condensed steam is m3. Whatever steam is going via the outlet, we don't measure it. Only the condensed mass of steam is m3. Okay. Latent heat of vaporization of water is L. Specific heat capacity of the material of the calorimeter, which stirrer, is S1, and that of the water is S2. Now writing the energy balance equation as we did in our previous cases. So heat gained by the calorimeter and heat gained by the water kept initially in the calorimeter is equal to heat lost by the steam in condensing as well as heat lost by the condensed water in cooling from theta 1 to theta 3. So from here we can calculate specific latent heat of vaporization L as like given in this formula, where total latent is given as m3 into L. Okay. Let's talk about mechanical equivalent of heat. So in early days, heat was not recognized as a form of energy, but calorie was defined as the unit of heat. So calorie is the heat required to raise the temperature of 1 gram of water by 1 degree centigrade, that is called 1 calorie. Now later experiment established that temperature can also be raised by performing mechanical work. That means we can raise the temperature either by supplying heat or otherwise doing some mechanical work. Now say mechanical work W produces the same temperature change as that of heat H would do, then W is known as J into H, where J is the mechanical equivalent of heat. When W and H are measured in the same units, then J equal to 1. So when W is measured in joule, there is work done by a force of 1 Newton in displacing an object by 1 meter in its direction is 1 joule. This is the definition of joule. Now W is measured in joule. Here J is expressed in joules per calorie because we are measuring heat in calorie. Then the value of J gives how many joules of mechanical work is done which is needed to raise the temperature of 1 gram of water by 1 degree centigrade. This is just the definition. Okay. So in summary, we have learned specific latent heat of fusion. Then we have talked about intermolecular forces, measurement of specific latent heat of fusion of ice, then measurement of specific latent heat of vaporization of water, and mechanical equivalent of heat. What I suggest is, after watching this lecture, I would like to recommend you to perform some numerical of our textbook, HCB, chapter number 25. And there a lot of example numericals are there, also exercise numericals are there. Then you will get to know the concepts better. So by now we have covered 3 chapters, and mostly we have talked about heat as a form of energy, then different postulates of kinetic theory of gases. But mostly kinetic theory of gases are some calculations are related to kinetic theory of gases, which we will learn in our next few chapters after the thermodynamics is covered after this chapter. Okay, in this chapter we have learned about the calculation regarding heat, which is also very important. And in some of the question they will combine all the big module of thermodynamics will be combined, and mostly they will ask question like that. Okay, thank you.